Okay, so good afternoon, everybody. Today, I would like to share with you an interesting item or subject for this lecture. And I introduced the item last time, but I want at the moment to go more in details of these issues. Okay, so the point is the following. We have to solve for stability, for example, for linear aircraft analysis. When I say aircraft, I have in mind a flow, a translating aircraft, not a maneuver, with a vibration around this steady developed solution. So linear aircraft analysis. And at the end of our modeling description, we have the following equation for discussing the stability. And we have a dynamic pressure, we have the aerodynamic matrix, and we have here the Laplace variable and the flight parameter. And our equation is reduced to solve the value S value here Sn and here Sn and here W. We have to find Sn such that determinant of this equation be 0, and then we go back here to find the eigenvector. I have a suspended point for these issues in the sense that I have to convince you that the free response of this problem is given by, again, is given by a combination of such an eigenvector multiplied by Es and this Sn by T, and therefore this here we have some constant depending on the initial condition, and this demonstrates that this object here, Sn, are exactly the key constants necessary for demonstrating the stability or not stability of the system. So we have to solve this problem. And I show you this later shown. But at the moment we have to solve this equation. We have two possibilities for solving this equation. The first possibility, and this is not a standard eigenproblem. In fact, this is not a standard eigenproblem. Because in the case you don't have aerodynamic, structural dynamic, you are able to solve this system and you will have as value for Sn square, you have omega here, you have omega minus omega square n, and therefore your pole 1, 2, n are plus minus j omega n, and this omega n are the mode of vibration, and this can be simply solved by taking the determinant of this equation And in this case, this determinant is a polynomial equation. And that's all. But in this case, you have a standard eigenproblem. This is standard. This is standard. Because in MATLAB, for example, for solving this equation, you may find the package able to solve K, and here you have the eigenvector, the real eigenvector, or mode of vibration. And in MATLAB, you simply have to solve the following. And here you have omega square positive. Pay attention to the role of this minus sign, okay? On defining the eigenproblem and on defining the Laplace transform of this. Okay, as this is standard in MATLAB, this is a two-matrix eigenproblem, standard again. But here we have this. This is not standard at all. And in general, we have a black box giving you the aerodynamic matrix E whenever you have a value, a complex value S for your matrix. Okay, so you can call the solution, you can call the evaluation of the E matrix whenever you have an S value. And so you can have, for example, an iterative procedure. For finding Sn and Wn. And we will talk about this iterative procedure, which are the procedures also available in the commercial package. But you have an alternative here. An alternative is an approximation for the matrix E. So express this matrix as a function of this frequency as by using an interpolating form, and this approximation, this second possibility, has the advantage to describe the elastic system. The main advantage is to describe the aeroelastic system in a state space form. And this is what I told you past time in the previous view graph. Here we want to express our aerodynamic matrix in frequency domain by using an expansion in the reduced frequency. And so this is a phase of this approach, but the other phase of the medal is that whenever you do this, you will be able to represent the elastic system completely in a state space form. Sorry, as a differential, as a system of ordinary linear differential equation on time. Okay? Okay, so let me do in detail about this. Okay, we want to talk about this item today, and we want to start by our aerodynamic matrix as not as a function in frequency domain, not in Laplace domain. And at the origin, we have this matrix as a function of omega and u infinite, but we can introduce the dependency direct dependency on the reduced frequency, defined like omega L, or if you want, C by 2, taking as a reference length the half chord, divided by U infinite. Okay, and introducing this variable, we have that this E is the unique independent variable for our aerodynamic matrix. Now, imagine to approximate this dependency by K in the following form, assuming some fixed matrix like A0, fixed, I mean constant matrix, A0, A1, A2, and something else like IK, and something else like A2 plus M, and then in particular we want to fill this interpolating structure in this way. We have a constant term plus a term, a complex term depending on JK, plus the square of JK, and then here something different like a summation from 1 to M, like M poles of the structure divided by JK minus a number, a fixed number like beta M. So what does it mean? We have, we hope to interpolate our data by this structure, in the sense that, for example, imagine to have the frequency domain axis, and here the value of the aerodynamic matrix, a term of the aerodynamic matrix, for example, ij, one term, as a function of k. I imagine to have here the real part of this, like this, and the imaginary part of this, red, like this. So I'm assuming that our matrix, aerodynamic matrix, is decomposed in real part, because it's a complex matrix, a complex valued matrix, plus J imaginary part matrix. Function of K, both of them, okay? Next, imagine to have evaluated this matrix in fixed point of the frequency. So this cross value are the evaluated value. Excuse me, here, 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 here. So this is evaluated by computer. How? Exactly by the theory we have developed. So I have developed the theory, and I have the capability to evaluate my aerodynamic matrix for prescribed value of the reduced frequency, like this, 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 and this. Okay, so these cross are my computing data. Now I want to determine this matrix coefficient, this, 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 and this, to be determined. How? I want to show how. However, I want to go in detail in this approximation. So you have here something acceptable because this part here is a part very, very similar to have a stiffness, a damping, and a mass matrix. Why stiffness, damping, and mass? Because we have here a multiplication by jk, or frequency or Laplace domain variable, to the power 0, power 1, power 2. So when you multiply and apply this aerodynamic matrix to a state space variable, you should have first derivative, second derivative, and zero derivative of the state space vector. So this part here is something associated to the quadratic part or non-circulatory part of our aerodynamic matrix. We talked about this here. Yes, when we analyzed all the matrix contribution as a product, 4 by 3 by 2 by 1, we conclude that as we have a linear dependency on P, linear dependency on P, and a transcendental dependency on P, when we take the product, al maximum we have up to second level degree polynomial dependency, and something else strange, because we have here an exponential by P. Okay, so for this reason, we assume as interpolating structure a structure like this. And this is the strange part, and this is the polynomial part. But remember, we don't know A0, A1, A2, and here we have A3, A4. Next, I want to discuss this part. Excuse me, I forgot this multiplication by IK. Okay, and I also want to discuss this beta m. What is this beta m? You know that for JK, note that this JK is the Fourier part of our Laplace part, which is represented by P, the n-dimensional P. Okay, so for JK equal to beta, we have a pole. This beta is a pole, is essentially a pole, is an assigned pole, is something located in the, here you have the real part of P, and here you have the imaginary part of P. P is equal to alpha plus JK, and therefore this beta is representing a pure real negative pole, like one here, beta 3, and so on. These poles are assigned. Assigned pole like to be assigned in this way. Beta m is equal to minus omega max L. Excuse me, I have to. Excuse me. Okay, so this pole is assigned and is equal to a maximum frequency of your problem. So if you multiply this by maximum frequency of the problem, omega, like omega max, by L divided by U infinite, and divided by M, so you have a first pole here is equal to minus omega max by L divided by U infinite, and a second pole here equal to omega max L by 2 U infinite, and again the other. So you are currently assigning poles for your aerodynamic here by assigning this beta m, and these poles are real and negative, and the rest of this expression is composed by a matrix coefficient like a0, a1, a2, and am plus m. And the point is, how can you calculate this coefficient? How can we calculate the matrix coefficient? In the sense that they are matrix coefficient of this aerodynamic matrix representation. We have data here, and so we can minimize the distance between. So the answer is the following: by minimize the distance between the data and the interpolating structures. So applying a minimum criterion, period. And so we have to define an error, and the error is very simple to be defined, because we can introduce an error matrix E epsilon, which is a function of consider that this value are the value are K1, do not consider this, K2 are the value where the aerodynamic matrix is evaluated, K1, K2, K3, K4, K5, and so on. So we have an error matrix depending on the K reduced frequency evaluation Kn. So we have AKN, and the AKN is defined as error matrix equal to the exact value of this term as EKN minus the value of the interpolating or approximated structure. The approximated structure is this structure, is this value here. This value is the E approximator. This is almost equal. This is equal to an approximated structure. It's a function of K. Okay. And when you take this difference is equal to the value of the matrix evaluated minus 80. I am subtracting the approximate structure, 80 minus IKN by A1 minus IKN to the power 2 by A2 minus summation of M from 1 to the number of poles IKN by A M plus 2 divided by ik and minus beta n, like Miller. Okay, so we have an error matrix, which is a function of the unknown matrix coefficient, like this, this, and this, which are unknown. This is known. Okay, and we have an error matrix, but in order to implement an optimal algorithm for finding the coefficient, we have to define a scalar vector, not a matrix, not a matrix error, but a scalar error. And in order to have a scalar error, we define this scalar error from this, and the scalar error is equal to the matrix inner product between the error matrix E epsilon function of Km, and this is a complex matrix. We can multiply this matrix by the conjugated matrix, and this double dot here means that we are multiplying the 1 term by the 1 term of the conjugated here, so obtaining a scalar number, and we are summing all the elements of the matrix, summing all matrix element. And we have also to sum all the reducer frequency value, key 1, key 2, key 3, all the data available from 1 to n data. So we have a scalar error. If you consider this scalar error definition, this scalar error is a quadratic function of the AM matrix. Go to the other slide. Our scalar error is a quadratic function of a 0, a 1, a 2, and blah blah blah. Okay, so if we impose the stationary condition with respect to the A matrix, A0, A1, we can obtain by this optimal problem value of A0, A1, and so on. Okay, so this is the procedure. This procedure is very similar to the determination of, for example, of regression straight line. This is a standard case. For example, straight line, very similar. In the case of regression straight line, you have the following problem. You have couple of value for x and y, like this. You have couple of data. You have x1, y1, x2, and so on. And you want to determine the best, in the minimum error sense, the best straight line, like this, interpolating this data, like y equal to mx plus q, and you want to determine this m and this q exactly in the same way we are determining our matrix A0, A1, and so on. So minimizing the distance between for each data. You have this data, for example, and you want to minimize the distance between the straight line and the point. This point here is x3, y3. You want to minimize this distance, which is y. This distance here is, in this case, is mx3 plus q minus y3, which is this ordinate minus this ordinate. And you can sum all this data and asking for, so summing here for m data summation, but you want to minimize the square of this error because you want to be sure to consider the same way an error in this side with respect to an error in the other side of the straight line. Okay, so you prefer to minimize the square of the error and ask to be minimum or stationary, better, with respect to, in this case, with respect to q and m. And you have clearly a quadratic expression in terms of q and m, exactly like here when we, after this error definition, we have a quadratic expression for the interpolating matrix A0, A1, and all the other matrices. Okay, so this is similar to the term the regression straight line or any kind of regression curve. Okay, and so we have this kind, after this minimum error process, we have the matrix A0, A1, A2 ready to be used here. But a point of this kind of description, a critical point of this kind of description, is that the poles are assigned and not part of the process. If you included also the beta as announced in this interpolating process, probably you will have a very higher or larger space for finding your optimum interpolating structure. But if you include this beta as unknowns, your minimum error problem probably could be not a linear problem, but a nonlinear problem. In fact, when you consider this error, our final equation here, stationary, means that you have to take the derivative of your scalar error with respect to any term of your matrix, for example, with respect to 8, 1, 2, and put this equal to 0. These are the equations you have to solve for finding your stationary point. But since the scalar error expression is quadratic in A, when you take the partial derivative, you have a linear equation in A0, A1, and so on. So the equations are linear linear with respect to a unknown, all the unknown, a0, a1, a2, and so on. And this is a very advantage on using this kind of approach. But the disadvantage is due to the fact that you don't have the polars unknowns, so your stationary point is not so optimal. It's not so optimal with respect to the case when you consider also beta. But if you consider beta as an unknown, your minimum problem is not reduced to find a solution for a linear problem. You have a nonlinear problem to be faced. So we have another kind of proposal of this approximation. We have another, after these critics, we have another proposal for interpolating structure. Is the following. We have E matrix as a function of K approximated by another approximating form I want to call like approximation 2, where approximation 1 is the previous one. Here, this is the approximation 1. Okay. Yes. And in this approximation 2, we have the same initial part, because we are convinced that this initial part is as a physical meaning, and therefore this part, like the matrix A0, A1, A2, has to be kept in also in this new approximation. And so we have jk here plus jk to the power 2 here, and here we have the difference. And the difference is the following. We have to consider identity matrix by jk minus p, excuse me, which is a matrix, which is a matrix of poles, something like that. So P matrix, and this structure is here to the power -1. So this is just like a denominator in quote, a matricial denominator in quote. And here we have a numerator like R numerator by jk, jk, jk. jk. Okay, so this is my new proposal for our interpolating structure. So we have this part which is the same, and here we have, look, a matricial form of something like this. Look here, R S Laplace variable divided by S minus P. So S is the Laplace variable, so a fraction with a number at the numerator R and a number here, so representing the pole of this fraction. So we have not a polynomial, but we have a fraction, a matricial fraction with R and P matrix to be determined in my process. Okay, so we have this new interpolating structure, and for determining this new interpolating structure, is new interpolating structure single. We have the following. We have that E, we have that an error matrix, which is the value. We have an error matrix, a new error matrix, which is the data minus the interpolating structure, so minus ikn to the power 2 by a2 plus ikn by a1 plus a0 plus ik identity minus p, and I want now to write our no matrix. Here we have a2, a1, a0. Here we have p to be the term now, and again we have ikn by r. So in red we have the matrix to be the term in our process, and this is the error. However, if you consider this error matrix, the data, this is the computed data, and this is the interpolating function. If you take in this error, you have this denominator here, and when you take the square of this to be minimized, you should have a nonlinear contribution given by this denominator here. So the trick is not to consider this error, but in order to have a linear problem, for searching the matrix coefficient, multiply this error expression by this structure here, by this, pre-multiply all the expression by this term. Pre-multiply by iki minus p. And then we have here a new matrix error by this operation, which is the matrix error E epsilon kn error matrix, which is equal to ikn identity minus p multiplied by this, the data kn minus 80 minus ikn by a1 minus ij or ikn to the power 2 by a2, and close this, and then we have minus ikn r. Okay, so this is our error matrix, and after this definition uh, this is better. This is better because this kind of problem is such that when you define as a scalar, now as a scalar error, you have to simply define summation with respect to the data and n from 1 to n data, and we have the conjugate of this matrix dot dot kn, of course, dot dot the matrix E epsilon kn, and we want to impose this as stationary with respect to A0, A1, A2, P, and R. So we have here the advantage to have expanded your research space for our coefficient, in the sense that we have included also this pole matrix and this numerator matrix P and R, and after this determination we have a better fitting of our data. However, I won't conclude this lecture for you not showing at the moment the real advantage of this approach. However, at the moment we have as final formula, for example, for the case of approximation 2, for the approximation 2, we have finally described our aerodynamic matrix E as a function of K as equal to A0 plus A1 JK plus A2 JK, and at the moment we have already determined this coefficient matrix A0, A1, A2, and the other IJK identity matrix minus P matrix to the power minus 1, and finally JK by R. The interesting point is that if we know now your interpolated aerodynamic matrix on the imaginary axis, we can expand the domain, and this is important. We can now expand our... Scusa Dario, sto finendo lezione, 5 minuti di richiamo, proprio 5 minuti. Scusami, ciao ciao. We can now expand our domain to P, just substituting here. Look, instead of K we have P, instead of JK we have P, instead of JK to the power 2, I forgot this, to the power 2, we have P to the power 2, and here we have P, and here we have P. Next time, the day after tomorrow, in the morning, we have a recovery lesson. We start by this, that this obtained interpolation, and I will show you that starting by this obtained interpolation, we can write completely our elastic system in a fully state space form, only ordinary differential equation, but expanding our state space dimension, including new states, and the new states in our elastic system are formally the aerodynamic space variable, state space variable. Okay, so I stopped here, and I will go on the day of tomorrow in the morning. Thank you. See you. Arrivederci.